Welcome to lesson number 7 of the neural network section. Before we dive deeper into any more theory, what we'll do in this lesson is set up the initial stages of our project, which will consist of simply plotting two regions of data onto Matplotlib. To set all of this up, this entire lesson will consist of making use of Matplotlib and very simple NumPy. If you feel that you're already comfortable with NumPy and don't want to go through setting up the initial stages of our project, then feel free to download the code in the resources folder and move on to the next video where we discuss more neural networks. Going forward with neural networks, we'll be using JupyterLab rather than the Atom text editor, which will prove to be a lot more convenient and very similar to Jupyter Notebooks if you did the Python crash course. So what we'll do first is inside of the terminal, we'll navigate to Desktop, CD Desktop, and inside of Desktop, we will open JupyterLab, and we'll start a new Python 3 notebook. I will call my file, rename, logistic regression. And before we start, if at any point running the cells isn't working for you, make sure to shut down the current kernel session and then restart a new one. And back to our file, we'll minimize this and start off by first importing NumPy as the alias np, and we'll also import matplotlib.pyplot as plt. We'll run this cell, and this subpackage pyplot will contain many useful functions needed to plot our data. First and foremost, we're going to plot 200 initial points onto Matplotlib, 100 points for each class. And for the sake of clarity, we'll start with only 10 points. As such, we will set a variable, number of points is equal to 10. We'll start by displaying the points in the top region. So set our variable, top region, is equal to numpy.array. Since we're displaying many points, obviously these points must be contained inside of an array. Each point is going to have a random x1 value and a random vertical x2 value. Yet all the points have to be in the top region. So what we'll do is we'll first specify the x1 values. We will set a variable, random, x1 values is equal to numpy.random.normal. What normal will do is return an array of random normally distributed values. If we imagine a normal distribution, random points are distributed as a symmetrical bell-shaped graph. Looking at this curve, it starts at the center, the mean, and then spreads out over a wider range of values. Similarly, looking at the end result, and specifically at the top region, the center of our normal distribution for this region starts at 10 horizontally, since it looks like most of the points start within that region, and then it spreads out over a wider region. More specifically, our distribution starts at 10 and spreads out over some standard deviation. So back to our code, the center of our point distribution will be at 10. And the standard deviation, which is simply a measure of how spread out the numbers are, I'll put -2. You can make the standard deviation into whatever you want. You can make it bigger, like 3 or 4, which simply means that your points are going to be more spread out from the center over a wider range of values. I'm just going to leave mine at 2. And finally, the last argument is simply how many points we want in our distribution, which will simply be the number of points declared, 10. We'll go ahead and output the variable random x1 values, and it prints normally distributed numbers with 10 as the center of it. Now this array denotes how the points are distributed horizontally. Each point on the graph requires both an x1 and an x2 coordinate. We already distributed our points horizontally. Now we need a corresponding array that also represents how the points are distributed vertically, along the x2 axis, which ideally would start from the middle, upwards and downwards. Looking at the top region of the end result, the center of our points distribution looks to start at the x2 coordinate 12 and spreads over some standard deviation. So back to our code, we will set a variable, random x2 values is equal to numpy.random.normal with center 12, standard deviation of 2, and number of points 10. And now we can simply combine the horizontal and vertical coordinates of our top region into a single array. So we'll just put in the random x1 values and the random x2 values. And now that we have the x1 and x2 coordinates for 10 points, let's go ahead and print them out. The first row of data denotes the horizontal positionings of our points. The second row, the vertical positionings. The way our array is formatted currently is a bit problematic, especially once we get into matrix multiplication to calculate the areas in our linear models. This right here is the horizontal coordinate of a single point, and its corresponding vertical coordinate is on a different row. We need all horizontal and vertical coordinate pairs to be on the same row, such that each row will have 2 elements. What we can do is we can take the transpose. The transpose, as we discussed in the crash course, simply interchanges each row with its corresponding columns. The rows become the columns, and the columns become the rows, ultimately giving us our results. We can do this with either a .t or a .transpose, whichever one you prefer. They both work the same way. We'll go ahead and print this out. Both x1 and x2 coordinates for every point are on the same row. Now let's go ahead and display them with matplotlib. We'll write plt.subplots, which simply allows you to display multiple plots on the same figure, and we'll specify a figure size, fig size, which we're going to set equal to a tuple of floats, which will simply be 4 inches wide and 4 inches high. That's the size of our figure. And plt.subplots actually returns a tuple, which we can unpack into 2 values, fig and ax. And you know what? We're not going to be making use of the figure variable, so we'll just leave this blank. And we'll use our axes variable to display a scatter plot of data with ax.scatter. The first 2 arguments will specify the horizontal and vertical coordinates of our 10 points. For our first argument, the horizontal coordinates we're going to access directly from the top region array. And looking at the array, all the horizontal coordinates are in the first column, so what we need to do is access every single row by first referencing the top region array. And we want to index every single row, which we can do with the colon. And we want every row in column 0, the first column, so we'll specify an index of 0. If you're not familiar with indexing, make sure to refer back to the NumPy crash course. And now for the vertical coordinates, top region. Again, we'll use the colon to index every single row in the array, but we want every row in the second index at index number 1. And now, for the sake of concision, what we'll do is we'll declare our random values right inside of our array. Delete those. And finally, what color will our points be? Well, we'll declare a keyword argument, color, equal to red. R short for red. Final step is to simply show the plot with plot.show. Run your code. And there you have it, 10 points with the random horizontal and vertical coordinates. Let's make this into 100 points. Much better. Now we need to add the points at the bottom region. We'll do this rather quickly by setting a variable bottom region is equal to a numpy array, numpy.array. What we'll do first is specify the x1 values of all these points with numpy.random.normal. And looking at the end result, specifically at the bottom region, clearly the center, the mean of the normal distribution for this region horizontally starts at the coordinate 5, since it looks like most of the points start within that region and then spreads out over some standard deviation. So back to our code, the center of our distribution will be at 5. And the standard deviation I'm just going to leave out as 2. And how many points we want in our distribution is simply the number of points. As for the vertical coordinates, it seems that the distribution starts at 6 vertically and then spreads out over some deviation. So back to our code, we'll write np.random.normal with a mean of 6, standard deviation of 2, and the number of points is simply the number of points. Ultimately, we now have 100 points in the bottom region, 100 in the top, each one with random x1 and x2 coordinates. We just need to display them on our figure. But once again, let's take the transpose and then use our axes variable, ax.scatter, to display a scatter plot of data. The bottom region has the exact same dimensions as the top region, so let's just go ahead and copy that. And instead of top region, we'll write bottom. And our color will simply be blue. B short for blue. All right, let's run the code. and we get our two regions of data. Eventually we'll have our computer find a linear model that best classifies them. But before proceeding to that, let's make sure that whenever we run our code, we want our coordinates to stay the same. We want repeatable results. And thus we must seed our number generator. We can do so with numpy.random.seed0. By writing this line of code, it's just a way to get the same random numbers each time you run a program. That way, if there's an error in your model, we can reproduce the error every time. And if you keep running the code over and over, notice that the same set of points will appear every time. Simple enough. This was just pure NumPy and Matplotlib, nothing fancy so far. We have our two regions of data. The entire goal of our project will be to use this data to train and develop an algorithm to come up with a line that separates this data into discrete classes with minimal error. We'll start implementing that in the next few videos.